Alright, so today we are going to be doing geometry and we're going to be focusing on circle theorem. Okay, circle theorem. So we're going to apply some laws related to circles to find missing angles. We call this circle theorem. So I want you guys to take this down, then we'll start. So we need to figure out parts of a circle. So we need to understand the parts of a circle. So before we go there, what parts of the circle do you know?
The arc, the tangent, the radius, the diameter, and the sector.
Yes, that is some great. So you got others, but what you said is good. So that shows that you have a understanding of the verbiage used when it comes to circles. So it's going to be very important when you make references to things in the circle to use that verbiage, especially when it comes to explaining what something is. So these are the parts of the circle that we have here. So we have the diameter, which is one point touching on the circumference, passing through the center of the circle and going to the next part of the circumference. Alright, and it's a straight line. The radius is from the center to the circumference, which is basically half of the diameter. Now, any other line that touches from one point to the next point of a circle is considered to be a chord. So in essence, a diameter is some form of a special chord, but anything that does not pass through the center is referred to as a chord. Once it passes through the center, we call it a diameter. So we could also have a line touching outside the circle as well. This line, we call it the tangent. So this tangent touches the circle at one point outside of the circle. Then we have the other side here. So if we have an arc, so this arc is like a portion of the circle itself, or the circumference going straight around, right? So the arc is a portion of the circumference, or the full distance around the circle. So from here to here, for instance, is an arc. Now if we have an arc and we draw a line touching where the arc starts and where it ends, this portion we would call it a segment. Okay, so as you can see here, here's a chord and here's an arc, and together they form a segment. Now on this side here now, you see that we have two radii. So you have a radius here and a radius here, and it's closed, or what we say subtended, by an arc. Once you see that, it's called a sector. So a sector is like a slice of pizza. Alright, so I want you guys to take this down. Make sure you draw this down, because this is something that's going to be important when it comes to you understanding this topic moving forward. Alright, let's go to the next one. Segments and arcs. So we have minor arcs and major arcs. So obviously a minor arc would be an arc that is less than half the size of the circle. And if the arc is bigger than half the circle, we call that a major arc. Okay, so from here to here would be a major arc. Now likewise for the segment, if we have a segment that's smaller than half a circle, we call it a minor segment. If it is larger than half a circle, we call it a major segment. Alright, so I want you guys to take this down so you can have a visual understanding of what these are. Alright, so we're going to look at some keywords. So this first one here is subtends. So when we say subtends, right, this is a line, a arc, a shape that closes an angle. Okay, so when you say subtends, that means something that encloses an angle. So let's make a reference. If we had this angle here, it's a 90-degree angle. So I could say that this cloud here, so this is a cloud that I have here, this cloud encloses this angle. So in other words, this cloud subtends this right angle. Does that make sense?
Yeah.
No. A line that subtends a right angle, we call that a hypotenuse. Okay? We call that a hypotenuse. But subtends is just basically encloses the angle. Alright? Now the next thing we need to know is a cyclic quadrilateral. So a cyclic quadrilateral, this is basically when you have a four-sided shape that all points of the vertices of that quadrilateral touches the circumference of the circle. Okay, so those of you who like pictures, as you can see in this case here, for instance, we have a square. Its vertices touches the circumference at some point. Okay, likewise over here, rectangle touches the circle at some point. Likewise here, these shapes touch 4 points of the circle. Same here. If one point does not touch, then it is not a cyclic quadrilateral. All 4 points have to touch. So if, for instance, this one here went from here to here, then went to here, and then go back here. And this is where the other point is. This is not a cyclic quadrilateral because all 4 points do not touch the circle. So I want y'all to take this down. This is very important, guys. So make sure you take this down. As you can see here, this 45-degree angle is subtended by the minor arc AB. Alright, so let's start with the semicircle theorems, right? So an angle subtended or angle closed by the diameter is equal to 90 degrees. So if you look at this, right, we have a circle here. This is the diameter. Now inside of this circle, so half of the circle, we have an angle. This angle sitting on the diameter forms 90. This was something that they realized. If you was to draw a circle, draw a diameter, and try to draw an angle at any point, it's going to be 90 once it is sitting on the diameter. So as you can see here in this case, we have two different angles drawn. Even though they are two different angles, because they're both sitting on the diameter in that semicircle, so you see the angle must be touching the circle itself, we know that that's 90 degrees. All right, does that make sense?
Yeah.
So I want you guys to write this down and draw the diagram. Trust me, in this topic, it is very important to have a visual understanding of what's happening. All right, so when we find these angles, what we need to do as well is state the reason why. So for example, I'm looking at a triangle inside of a semicircle that encloses the diameter. Once it encloses diameter, I know that this angle here is 90 degrees. So right here is 90 degrees. So this here diameter enclosed by this angle is 90 degrees because, and this is where my reason becomes important, because an angle subtended by a diameter is 90 degrees. And we know that the angle itself here must be touching the edge or the circumference of the circle. All right, does that make sense?
Yeah.
All right, let's look at the next one now. Now, based on that knowledge, I want y'all to tell me the angle at this point and the angle at this point, because you know that all angles in a triangle add up to what? What do all angles in a triangle add up to?
180.
Good. All right, so I want y'all to focus on calculating these angles. When you're finished, send it to me. Anybody got it? Waiting for the answers?
Is 90 degrees, right?
Correct.
So 90 plus 23 subtract is 113, subtract 180. The B is 67 degrees.
Lovely. So we know that here is 90 degrees because this angle subtends the diameter. So because it subtends the diameter, it's 90 degrees. So we know that all angles of a triangle add up to 180. Okay, so A is 90, and now here is going to be 67 because 90 plus 23 is equal to 113. All right, so because all three angles add up to 180, we would literally say 180 minus 113, and that would give us 67 degrees. So here now has to be 67. Does that make sense?
Yes.
And we know this because this angle subtended by the diameter is equal to 90, and then the triangle, all angles in a triangle add up to 180. All right, so the next theorem, segment of a circle theorem. So what this says, it's any angles in the same segment and sitting on the same chord are equal. So in this case, you could imagine the chord being a line passing here, straight line, same thing as here. All right, so this here is almost like a spin-off from our first one here, right? So if you notice here, it's a fancy chord known as a diameter. So as you can see here, we have two different angles sitting on this line. Okay, so this particular thing, I call it the bow tie. So if you look at it, it goes like this. It looks something like this, right? Because you have this section here and it goes down here, comes here. This is another angle, right? So I kind of think of it, I look for something that looks like a bow tie. So the angle here is 90 and the angle here is 90. because they're sitting on the diameter. Now likewise here, this is like a bow tie here again now. So if you look at this here, this angle here, and then we got this angle here, sitting on this line is going to be the same. So 45 here, 45 here. So just like how it was sitting on the diameter to give 90, 90, in this case, whatever the angle is on one, is on the next angle here as well. And this goes both ways. Alright, so I want y'all to take this down and I'll break it down a little bit to show you a comparison and we'll go from there. So just to bring a little clarity, so we were saying, right, essentially, if you have a circle and connect the points, so this here forms a 90-degree angle. Now what we also saying is, if we was to put a next one here, if we put a next one here, this too also forms a 90-degree angle. Now if you check the outline of this, it looks like a bow tie. Okay, if you look at that. So from here to here to here to here. Now in that bow tie, the angles, because they're sitting on this line, here is the same angle as here. Okay, so where they sit is the same angle. Likewise, you could look at it from the flip side. So upside down here, whatever the angle is here is the same angle here. Okay, because this here now is like it's sitting on this line. So this opens up to this line, this opens up to this line. Now why is this important? This is a particular one. This is the one for sitting on the diameter, which means that here and here is 90. So now instead of 90, let's say we actually was coming from here. Alright, so this here is a card, and the card no longer was a diameter. Now even though this here is a different line, and remember I could not have this line too, but it doesn't mean that it's not a line here. They're sharing the same point here, which obviously means that it's an invisible line here. So that means the angle inside here is also the same as the angle inside here, just like this. So how here is 90, here is 90 when it's on the diameter. When it's sitting on something that's not the diameter, whatever angle is in here is also here. So with the one on the diameter, here is 90 and here is 90. Now with the one without the diameter, that's not on the diameter but on a card, and they both sitting on the same card, if this was 35, that would mean here is also 35. Okay, likewise, if you could look at it upside down, there's an invisible line here from this point to this point. So let's say for instance here was 20, this too would also be 20, because this here sits on this line. Even though it's hanging upside down, it's the same concept as if it was flipped the other way around. Alright, so with that in mind, this here technically has a line across here that represents the card, even though we don't see it. Alright, and likewise over here too. Okay, so based on that premise, what do you think the angle here is?
50.
50. Lovely, because this angle here and this angle here, they both sitting on the same card. Okay, now if here was 70, what would be the angle here?
70.
70, yes, because they are both sitting on this card here, just upside down. So this is going to that. Likewise, this here is going to that. Alright, and the reason why is because angles in the same segment and sitting on the same chord are equal. So remember, once you have this line over here, that means that this section here is a segment. Okay, this whole section here is a segment. Alright, with that in mind, trying to show y'all how to swim, I want y'all to work on these ones and send me what you got. And just to spice things up a bit, I want y'all to work this out too. Alright, so figure out what X is, figure out what Y is, and then work this out. So I'll give y'all a chance to try it. So two angles sitting on the same card, so you have to create a card for yourself to see. Two angles sitting on the same card are the same. Good. But I want you to write it down so you could have it. You need to be able to have it down. Okay? Alright, so let's go through this, right? So remember, these two here, they're sitting on the same card. So if you was to think of this as a card, okay, these angles here, bow tie, this is a bow tie, right? So the angles here are the same. Likewise, the angles here are the same. So in this case, this is 33. So here is also 33 degrees. Okay, now here and here is the same. So if this is 83, here has to be 83 as well. Because we know angles in the same segment sitting on the same card are the same. Okay, so if I wanted to find this angle here now, I could just add up all three of these. So all three of these supposed to add up to 180. So I can say 83 plus 33 is 116 degrees. So then if I say 180 take away 116, I will get 64 degrees. So that means inside here is 64 degrees. So both of these got the same angles. So here is also 64 degrees. So here is 64 inside this angle here. All right, so that's basically the concept of this. Does that make sense?
Teach that's always with a bow tie.
Yeah, whenever you got bow tie, this is what it does. You got it?
Yeah.
So far, we learned about the triangle in the semicircle. So the angle here is what? 90. And then we know that if we have two angles sitting on the same card, looking like they form a bow tie, we know that in here and here would be the same angle. Likewise, here and here would be the same because they are sitting on this card here. Alright? Alright, so this next one is called the center of a circle theorem. Center of a circle theorem. So this here, I call this the Patrick. Okay, so Patrick from SpongeBob. Alright? This says that the angle subtended by an arc. So this angle here, subtended by an arc at the center of the circle. So we have this angle here. So this angle here, which is closed by this arc. So basically this sector here, the angle for this sector is twice the angle subtended by the same arc at the circumference. So if you look at this, this is the angle here coming from the circumference. So this here by the sector is double the angle here. So if here is 100, that means here has to be 50. So I call this Patrick because this looks like Patrick standing up. You know, Patrick from SpongeBob, that looks like Patrick standing up, okay? So imagine that was Patrick. You know, he got his hand here. That's Patrick, all right? Now this one here is also Patrick, but the difference is Patrick is doing a toe touch. Patrick like he dancing, and that's his hand, then his leg touching, cause he jumping in the air. Excuse my diagram, it's horrible. But yes, it's like a toe touch. You know, he's doing a toe touch. This is his leg, and this is his hands coming from his head. So if you look at this, here is 2y and here is y. So for instance, if here is 200, we expect the angle here to be 100. So I want y'all to take this down and we go through that. So you see here, this here is like Patrick standing up, his legs, his head at the top here. This is his head again, right here, and his legs. Okay, so this is what I mean, a toe touch. Alright, so if you can visualize it like that, it would help you to better identify it when you see it. So let's try this now. So I want you all to determine what the value of x is. What do you think the value of x is?
40.
Lovely, 40. Everyone understands that? 40? Because we expect here, this is Patrick standing up here. If here's 80, we expect here to be 40 degrees. What would be the value of a?
45.
45. Correct. And then we justify it with this explanation. Alright, so next, what is the missing angle here?
48.
48. Alright, so looking at this one, what is this one? If this angle here is 21, what would this angle here be?
42.
42, lovely. Because we expect this angle here to be double this one here. And we know the reason is that the angle subtended by an arc. So the angle here at that sector is twice the angle of right here subtended by this circumference. The same arc at the circumference. Alright, so what is the missing angle for B?
90.
90. Lovely. Alright. Alright, so looking at this one now, if this one here is 110, what would be the angle here? This is the same concept, but does that Patrick is doing a toe touch. Okay, so if this is 110, what is here?
220.
220, yes, because it's double. So that there is the toe touch still. Okay, so this is his hands and his legs, he jumping. So here is 220. So if here is 120, what is the value of C?
240.
240, lovely. All right, so what would the angle be at B? Just trying to see if y'all remember from the previous question.
90.
How do you know?
Because it subtends the diameter.
Correct, it subtends the diameter, so it's 90. And then we can get X by adding 90 and 55 and then subtracting it from 180, which would give us 35. All right, so the next theorem we have here is the quadrilateral theorems, right? So what this says is that once you got angles that are opposite on a quadrilateral, so for instance, once it's a cyclic quadrilateral, opposite angles add up to 180. So this angle here and this angle should add up to 180. Likewise, this angle here as well as this, they both should add up to 180. All right, so just to give you a little clarity on that, so say for instance we had the angle here that was, let's say, 80. That means the opposite angle here should be 100 because two of these supposed to add up to 180. Likewise, if you had here 85, let me use an easier number. If here was 60, I would expect here to be 120 because the opposite angles should add up to 180. Likewise, opposite angles add up to 180. All right, so I want y'all to take this down and then we'll go through some examples. All right, so I want y'all to think about this one. What is the missing angle here?
99.
How did he get that?
Minus 81 from 180.
Yep. So you know this because from here to here we expect two of these to add up to 180. Likewise, we would expect here and here to add up to 180. So we would say 180 minus 81, which is equal to 99. So I know here is 99 degrees just because once we have angles that are opposite in a cyclic quadrilateral, they should add up to 180. Okay? All right. So we have different ones for y'all to figure out now. I want you to calculate the angles of A and B. All right. So what we got? So with this, both of these supposed to add up to 180. So then I would say 180 minus 140, which is equal to 40 degrees. So that means the value here is 40 degrees. And I know this because cyclic quadrilateral, so it touches all 4 points touch a circle. So as you can see, all 4 points touch a circle. So therefore, this is a cyclic quadrilateral. Okay, so these opposite points are 140 and 40 because they add up to 180. Now these opposite points here now, so 60 and A. So for A, that should add up to 180 as well. So 180 take away 60 gives me 120. So I know that this angle at A is 120. So the next quadrilateral theorem. So it says the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Because essentially this is the same thing as what we were doing. Alright, so let's explain this. So we know that the quadrilaterals that are cyclic, opposite angles add up to 180. So let's say for instance here is 120. So if here is 120, we expect here to be what? What would here be? If this is 120 and this is a cyclic quadrilateral, what would be the angle here?
60.
60. So if this is 120 and here is 60, we know also that here's a straight
That means the other be 120.
120. So this here's a straight line and these two lines here. So let's say this is this line here. We have 60 on this side. So the next side is 120 because two of these also have to add up to 180 because it's a straight line. So if with that being in mind, that's how we know that here's 120, here's also 122. So basically the principle before is used to apply in this instance here as well too. So it's just a spring off of this principle that we did before. All right. So what we want to work on here is calculating the angle of Y and Z. All right. So I'll go through my process of going through this. So I always ask myself based on what we learned so far, the first thing we learned was a triangle. And that triangle was the one with a semicircle sitting on the diameter. After triangles, what did we learn? Bow tie. So that's the next one, the bow tie. Then after that, we learn about Patrick. And after Patrick, we learn about quadrilaterals. Alright, so what I do is ask myself, do I see any triangles here? I do not. I do not see any bow ties, but I do see Patrick. If you look here, look Patrick right here. This is Patrick right here. So right here, I have Patrick. Can y'all see Patrick?
Yeah.
Then the next one is a quadrilateral. A quadrilateral. So from here, come down here to here to here is my cyclic quadrilateral. So I have quadrilaterals as well. So now in my head, I need to be focusing on what I know. So I know about Patrick. So I know when it has a Patrick, that means the angle right here is double this angle here. So if this is 40, this y should be what?
80.
80 degrees. Now, for the cyclic quadrilateral, the points that touch would be here, 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 and here. What do we know about the angles opposite of each other in a cyclic quadrilateral? What do they add up to?
180.
Lovely, 180. So therefore, you could say 180 minus 40 gives us 140 degrees. So right here would be 140 degrees because this here is a quadrilateral. So what happened here is we had two separate theories that we learned so far. We had a Patrick, we had a quadrilateral. So I say, okay, Patrick, boom. So with Patrick, I know that this here supposed to be double. Okay, so I solve that. Next one, quadrilateral. So I shape my quadrilateral, this outer four parts, and I know these outer angles here, these angles here, opposite of each other, should add up to 180. So I want y'all to take this down, and then we're gonna go through another example that y'all will try. So I want y'all to try this, calculate the angle here, and angle of Z. Let's go, write it down and try it. Alright, so let's go through this, right? So, same process. We look for triangles. Do you guys see any triangles in here?
No.
No. Any bow ties?
No.
No. Do we see Patrick?
Yeah.
Yes. Do we see quadrilaterals?
Yeah.
Yes. So, what do we know about Patrick? Here is 150. We expect here to be what? 75, yes. Excellent. So if here is 75 now, we already finished Patrick now. The next part we have here is the quadrilateral, cyclic quadrilateral. Notice here's a quadrilateral too, but it's not cyclic. We want this point to touch here. Like you see this point is touching here, so we have all 4 points touching the circle. Alright, so with these 4 points, I know that these opposite angles, so if this is 75 degrees, what is this here? So 75 plus this should give us what?
180.
180, lovely. So two of these should add up to 180. So we said 75, we subtract that from 180, and we get 105. Therefore, the angle here is 105. Remember, this part is a cyclic quadrilateral, but inside here we have a Patrick. Alright? And obviously, we will state our reasons why we know that these are the answers. Alright? So I want y'all to take this down. This is always my process. Obviously, we have some other stuff to learn, tangents and so forth, but for now, we're using what we know. Alright? So let's see you guys take this down, and we go to our next one. Alright, let's see how y'all do this one now. So with this here now, we check again, same concept, triangles. Then we look for bow ties. Then we look for Patricks. Then we look for quadrilaterals, cyclic quadrilaterals. So do we have any triangles here?
Nah.
Any bow ties?
Nah.
Any Patricks?
Yup.
Any cyclic quadrilaterals?
Yup.
So what you notice here is that if we look at this one, this 100 here is part of the cyclic quadrilateral. And we know that once the angles are opposite each other, they should add up to 180. So if this is 100, 180, take away 100 is 80. So the angle here should be 80 degrees. Alright, so we know he has 80 degrees. Now we have Patrick to deal with. So with Patrick, if he has 80, what would be the angle here?
160.
160, because the angle here is double this. So I would expect here to be 160. All right, and obviously you'd have to state your reasons why that is the case if you are in a situation like this. If we're saying in terms of x, we know here is x, here is double this, so y would equal to 2x. 180 take away this x here, so 180 take away x would give us the answer for this right here. Okay, so essentially that's what happens when we do this if we were to get it in algebra form. All right, so let's see what y'all would get for x and then for y. All right, so now you have to ask yourself, are there any triangles? Are there any bow ties? Do you see Patrick? Do you see a cyclic quadrilateral? Let's see what y'all get for this one. Let me see what I have after this one. It's 20. Good practice in here. All right, nice. All right, so let's see what y'all would get for this. All right, so let's go through this. So, as we always ask ourselves, triangles. Do we have triangles? Do we have triangles here?
Yes.
Yes, we do. Do we have bow ties?
Yes.
Yes, we do. Do we have Patricks?
No.
No. Do we have quadrilaterals, cyclic quadrilaterals?
No.
All right, so with triangles and bow ties, so remember with bow ties, this here's our bow tie. So I know that the angle here is the same as the angle here. So if here is 42, because two of these angles sitting on the same line here, or the same chord, this here is also 42 degrees. Does that make sense?
Yeah.
Now what you have to see here is this angle y. So this is inside of a triangle. So we know this angle, we trying to figure out this, but can we figure out the angle here? Remember this angle here is sitting on the diameter. So this is the diameter and this angle here is sitting on it. So that means that the angle here is a 90-degree angle. So here is 90. So then I could say 90 plus 42 is 132. So 180 subtract 132 gives me 48 degrees. Therefore, right here is 48 degrees. That's my answer. Alright, so you guys could take this down if you don't have it already. Alright, next one to try. See if you can calculate the angle for x and y. But I'll give you a hint. You will need to calculate this angle here. Okay? Now the thing is, because we have Patrick here, remember these two lines here are the radius. So that means the length here and the length here are the same. So this length and this here is the same. So that means that the angle here and the angle here are the same because it's an isosceles triangle. So when we have an isosceles triangle, the angles here are the same. However, that does not mean that this here is the same as this, okay? So first of all, you need to figure out what this is, and you need to figure out what this is to help you figure out the other stuff. Let's see what you guys come up with, then we'll go through it together. Alright guys, you ready to go through it? Alright, so same thing again. Do we have triangles? C1 here isn't any much use to me. Bow ties, Patrick's, quadrilaterals. So yes, we have a quadrilateral outside here. Alright, so to find this out, this is 44, so this one is going to be double with this Patrick story. So here's 88, and what you realize is that these triangles, three of these add up to 180. So 180 take away 88 is 92 degrees. But remember, two of these here are equal because it's an isosceles triangle. So that means we have to divide these by 2, which is 46. So that means here is 46, and here is also 46. Now, if you look at this, outside here is a quadrilateral. So this part here and this part here, both of these supposed to add up to 180. So right now the angle inside here is a collection of 32 and 46. So 32 plus 46 is equal to 78 degrees. So this full angle here is 78 degrees. So over here now, two of these supposed to add up to 180. So I could say 180 take away 78 gives me 102 degrees. So right here is 102 degrees. Alright, so this last piece here, we know here is 78, but this here is like a triangle. Okay, so I'm gonna put a different color for that so you can see it. So this here is a triangle now. Okay, so here's 44. This full thing is 78. So this piece here and this 46, all these three angles, this full 78 is 32 and 46. This, all these here should add up to 180. So I already add these up already, so I know that is 78. Then I could say 44 plus 78 plus 46 plus y, which is this. We don't know what that is yet. All of these should add up to 180. So 44 plus 78 plus 46 is 168 degrees. Okay, so 44 and 46 is 90. 90 plus 78 is 168. So 180 minus 168 is 12 degrees. So that means y is 12 degrees. Right here is 12. Because essentially, that's a triangle that we had here. So here's 44, here's 78, and here is a split of 46 and 12. Alright, so take this down. So we continuing from this. So we have alternate segment theorem. So the alternate segment theorem. So this here, the angle between a tangent. So this is a tangent here. And a chord. So this is a chord here, for instance, right? So this chord here. So the angle between that tangent and that chord at the point of contact is equal to the angle subtended by the chord in the alternate segment. So the segment here is this here. But then this here, everything on the right of this line here is the alternate segment. Okay, so this here is an alternate segment. This here is a segment that this angle is in. So what it's saying is that this angle here is equal to this angle here, which is an alternate segment. Okay, likewise, this angle here would be equal to this angle here. So this occurs when you have a triangle and a tangent together. So if you look at this here, for instance, so this here between the angle between the chord and the tangent is the same as the angle right here, which closes that same chord here. So this is 54. Likewise, here is 54 as well. On the flip side, here is 62, and here is also 62. Now, if we wanted to find this angle inside here, all we need to do is add these up, figure out what they are, because a straight line is supposed to add up to 180. Alright, so I want y'all to take this down. Then we try some examples like that. Then we go to tangent, and that's the last thing that we have to do as it relates to circle theorem. Alright, so what do you think the angle would be at x?
47 degrees.
Correct. So if you look at it, right, once you see this angle here, this angle will be the same. So it doesn't matter how the triangle look. It could be a small little tiny triangle here. It could be a big one here. But once it's a triangle in general, once you have the tangent and you have this right here, you know that this here is the same angle. Okay. Alright, so the reasoning will always be the same, because the question is usually going to ask you your reasons for it. Alright, so the thing is now, I want you to look at this one here, try to figure out what x is, what y is. Okay, so take this one down and actually try this one. Alright, y'all ready to go through it? Yeah. Alright, so what would be the angle over here?
80 degrees.
80 could be somewhere. Let me ask you, did you say 80 because you walked out that this was 80, right? And then thought it was the same one here?
I was thinking that they were alternate.
Okay, so I know what you're thinking about. You're thinking about this. So there's a different thing here, right? So if you look at this, there is a theory here, like alternate angles. So if here's 80, here's also 80. Okay, you remember this?
Yeah.
However, when it comes to this in circle theorem, when we talk about alternate, you're thinking of it in terms of segments in this particular one. So let's say, for instance, in here is a particular segment. Okay, over here now is another segment. So this is a different segment altogether. So this angle here, that is 80, and this is 80 because, 40 plus 60. We'll go through this part over again step by step. But because here is 80, the alternate segment, so if you're looking at this, the alternate segment is in here. Because remember, this is in the blue segment right now. So the alternate segment is over here. So here's where you expect it to be 80. Okay. Now down here, we know that down here is 60. And this is the car that makes it separating that segment now. Okay, so out on this side of the segment is 60. So the inner one here would be 60. Make sense?
Yeah.
Yeah. So essentially, with this here, what we could do with the alternate segment, so we know that this here is the angle here, 60. So if this is the angle, the alternate segment would be over here. So I know that this here should be 60 degrees. Now I could work this out two ways. Now I could add up all of these and try to figure out what this angle is. Because 60 plus 40 is what? What's 60 plus 40?
100.
100, lovely. Then we do 180, which is the total angles in a triangle. Subtract, and we get 80%. 80 degrees. So here now is 80 degrees. So now we got 60, 80, 40. Also, I would have realized that here, since here is 80, alternate angle in that segment would be also 80 as well too. So that's one way to look at it. This is one of the interesting theories, so to speak, and it is a bit tricky to some extent to identify, but when you do identify it, you could kind of be like, oh, that makes sense. But most times the ones that we did before would be the ones that you heavily depend on. So you could take this example down. I want y'all to take this example down, and then after we go to the next stage. Alright, so just a refresher from our last exercises. Let's see if y'all could figure out this here. Anybody get the answers? Let's see what y'all got. What's the answer for X here?
102.
102. How you get that?
Because of the thing, like the last example.
Okay, so this one here is from the quadrilateral story, right? But we know though that the opposite angle in a quadrilateral that's cyclic, these opposite angles should add up to 180. So 102 here would have been 78, because 78 plus 102 is 180. And then these two supposed to add up to 180 as well too. So here has to be 102. So because of that, that's how we know that this angle here and this angle here are supposed to be the same. What about this Q? What's the value of this Q?
88.
88 would be here. What would over here be now?
92.
Lovely, 92. So these two add up to 180, which is correct. And this here also adds up to 180. But remember, because we know here is 92, here would be 92 as well. Because here is 102, here is 102 as well. It's just a other theory that we have as well, but there are multiple theories. You use them accordingly to help you get the answers you need. So I kind of think of it almost like if I send you to the kitchen to eat some food. Depending on what it is, you may take a fork, you may take a spoon, you may take chopsticks, whichever you prefer, whichever you feel is the most beneficial for you to get your food completed, you would use it to eat. Likewise, with this, however you understand or best understand the principles, you're going to use it to your advantage as well too. Alright? So essentially, the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. So this here is similar to the alternate segment to some degree. It kind of uses the same kind of, concept, so to speak. Quite different, but still similar. Now, tangent theorems. We want to look at tangents. So a tangent, we know, is a line that touches a circle at one point externally. So the thing is, we have a tangent and a radius. Alright, so we have a radius here and a tangent. Note as well, this could also be a diameter, so it could be drawn straight across as well too. Okay, it doesn't just have to be the radius, but the whole point is must pass through the center. Once it passes through the center and then it touches a tangent, as you can see, what letter is this? What letter do you see here with the red and blue lines?
T.
Exactly. T for tangent. We know that the angle here would be 90 degrees. Likewise, the angle between here would also be 90 degrees once they passing through a radius or a diameter going through the center, okay? That's the only way you get a radius. If it's passing through the center and touching the end of the circle, or diameter, which has to pass through the center. If it's a other random line, the principle does not apply. So if we had a line that was going here, we cannot say that this is 90. It has to pass through the center. Then on this end now, we have to look at it here. Same concept. Doesn't matter which section of the circle it falls, as long as we get this set up here. Okay, we know that that is the case. Alright, so I want y'all to take this down. Alright, so this is a next tangent theorem. So what it says is the length of two tangents from an external point. So the external point is like right here, right? So this is one point. I would imagine this like a beak. So imagine this is a bird and this is its beak. So this is the top part of the beak. This is the bottom part of the beak. It connects to one point, but this is also a tangent because it passes and touches the line. Just imagine it's extending further along here. So that's how we have our T here. Okay, it's passing by the radius, so we know that angle here is 90. Likewise, if we had one extended here too, we would see that that also is a tangent. So we're saying that once it's connected from the same point, points of contact on the circle are equal. Alright, so when we go from here to here, the distance from these two and the distance from these two will be the same. So the length here and the length here are exactly the same. Alright, so tangents that intersect at a common point are equal in length. And opposite angles, therefore, of the quadrilateral formed add up to 180. So similar to the quadrilateral that's cyclic, we know that these opposite angles would add up to 180. The opposite angle here is this 90 as well as this 90. So 90 here adds up to 180. So whatever here is and whatever here is, two of these would also add up to 180 as well. Alright, so I want you guys to take this one down. That is the last theorem in the circle theorem that we look at this level, and we'll try to look at some of the questions from our assignment that we were supposed to look at. So even if you didn't get to do it, this is the time you'll be looking at it. Look at this here now, right? So based on what we just did, remember this here is a tangent. So we have our line here and it's coming from the center. So right here is 90 degrees. Okay, I want y'all to figure out what here is. So this one here as well as this angle here. So I kind of hint to you what one is already based on the rule that we just did. Let me see if y'all figure out this and this. Alright, so let's go through it now. So this angle here, what is this angle here, ladies and gentlemen? It's gonna be 90 because we have a radius here and we have a tangent here. Okay, so together these form 90 degrees. So here it's gonna be 90 degrees, just like here is gonna be 90 degrees. And then remember, these opposite angles should add up to 180. So 180 take away 48 is 132. Now the thing is, if this is 132 here, once you add up all four of these, you're gonna get 360. Now if here's 132, what do you think here is gonna be? Just remember in Patrick, the Patrick theorem we looked at.
66.
66, lovely. Because here is gonna be half of this. Now the next thing, these opposite angles, so what about here now? Because remember now, we have a cyclic quadrilateral here. So these opposite angles here, so 132 is here, these two should add up to what now?
180.
180. So here, remember we said that cyclic quadrilaterals, so if here is 66, here is 114. Because two of these should add up to 180. Alright? Alright, so I want y'all to open this. This is a work that y'all was supposed to do for me, so I want y'all to start working on this if you haven't already. If you have, just show it to me so I could see what y'all got.